Okay, hello there Year 10. This is a video to help you self-correct and improve on the electricity test. Now the first thing to say about this test was that it was fairly difficult for a foundation test. Here it is. So we're going to go over it step by step. So I'm going to be flicking between my answers and the mark scheme. So please, with a different coloured pen, preferably green if you've got it, can you self-correct? Also make an effort to follow along to try and understand bits that you didn't before, and write things down on your script, because I will be asking you at the end to take a picture of your corrected test, your corrected script, and upload it to show my homework, to show me that you've done this task. So you don't have to take a picture of all of it, but I am expecting you to take a picture of at least a couple of pages to show me that you have done the correction. So, okay, question 1. Difficult question this, we'll break it down into a bit. So question 1, a set of Christmas tree lights is made from 20 identical lamps connected in series. So here's the Christmas tree here, and the question continues. Part A, each lamp is designed to take a current of 0.25 amps. The set plugs directly into the 230 volt mains electricity supply. Write down an equation that links current, potential difference and resistance. So remember, potential difference, this phrase here, is just a fancy word for voltage. So the equation that you have to memorize and recall for the physics part of your combined science relating to this question is voltage equals current times resistance. So I've written it in words there. In symbols you say V equals I, remember I is the symbol for current in physics, times R. And in brackets I put the units. So in brackets V tells me voltage is measured in volts. The capital A in brackets tells me that current is measured in amps, and the R, resistance, is measured in ohms. So that was an easy mark. So that's correct. So don't even flick to the mark scheme to do it. Give yourself 1 mark if you said that. So next one, calculate the resistance of one of the lamps, show clearly how you work out your final answer, and give the unit. So this was a bit tricky. So basically, if you've got 20 identical lamps in series, I don't expect you to have drawn out a circuit diagram like me, but this is basically what's happened. You have 230 volts, this is a symbol for a DC power source, and your 20 volts are all connected, 20 bulbs, excuse me, connected all one after another down here, and you have got 230 volts across all 20 of them. So if you do 230 divided by 20, you get 11.5 volts across each one. You needed to do that calculation, 230 divided by 20, to find out the voltage across each bulb. Using your V equals IR, which was the equation it asked you to remember for the last question, the first thing to do was rearrange this for resistance. So resistance is equal to voltage divided by current. And if you can't rearrange equations yet, that's really, really, really important to work on in maths and science. So the voltage across each bulb you just calculated was 11.5, and the current through each bulb was 0.25. So if you do that calculation, you get 46 ohms. And notice that I always make sure that I write the answer with the unit on the answer line. So that was the correct answer. Flicking to the mark scheme, and we'll try and zoom in a bit here somehow. So the mark scheme is here. So 46 gets you 3 marks, and ohms gets you the 4th mark. If you have got 11.5 as a kind of calculation showing that you worked out the voltage across one of the bulbs, you get a mark for that. And if you get a final answer of 920, which means you've done the wrong calculation, you get 2 marks out of 3, so at least you get something. So let's go back to the test. Last one, what's the total resistance of the set of lights? So each bulb has a 46 ohm resistance, and you've got 20 of them. So 46 times 20 gives you 920 ohms. So I'll put the answer on the answer line. And part B, for 1 mark, how does the resistance of a filament lamp change as the temperature of the filament changes? So the relationship here to learn and remember is that as the bulb gets hotter, the little bit of wire which is producing the light also gets hotter. And so, you know, that increases the resistance of the bulb. So the hotter the filament becomes, the more resistance the bulb will offer, and that's something that you need to remember. So give yourself a mark out of 7. On to question 2. So question 2 is that you have to interpret this circuit. Now the first thing to remember is this is a parallel circuit. So this is your battery, 2 cells in series. The current comes out of the positive terminal, goes through the first ammeter, and then the current will split. And more of it has gone along the top branch, less of it has gone along the top branch through P, and more of it has gone along the bottom branch through the 20 ohm resistor. You measure the voltage across the 20 ohm resistor, but remember this isn't counted as part of the circuit, this voltmeter. The current recombines over on the right hand side of the circuit, and then the total current goes through the ammeter marked A4. So you had to fill in the gaps, so you had to find out what A1 and A4 is. So to do this, I transferred 0.2 and 0.3 above their appropriate ammeters on the circuit diagram. And if I have got 0.2 amps along here and 0.3 amps along the bottom branch, then the 0.2 add 0.3 must have entered into that junction and come through A1. So 0.2 add 0.3 is 0.5. So the answer to A1 is 0.5. Those two currents along those two branches would add back together when the current recombines over the right hand side of the circuit. So you would get 0.5 amps through A4 as well. And another rule to always remember is the current leaving the cell or the battery in a circuit will always be equal to the current returning into the negative terminal. So that's another rule which will confirm that A1 and A4 will both be 0.5 amps. So give yourself 1 mark for each one. Easy 2 marker there. So part 2. Which of the following statements is correct? Hit the correct box to indicate your choice. So 1 mark for the correct box and 1 mark for the correct justification. So was the resistance of P more than 20 ohms, equal to 20 ohms, or less than 20 ohms? How do you figure it out? Well, going back to our circuit diagram here, if you have 0.3 amps going through your 20 ohm resistor and you only have 0.2 amps going through P, it has allowed less current to pass through. And if less current passes through P than it did the 20 ohm resistance, the resistance must be more because less current has managed to travel through that resistor. So I have ticked the resistance of P is more than 20 ohms box, and that gave me a mark. And my explanation was a written response based on the words I just said. So the branch with resistor P on is allowing less current than the branch with the 20 ohm resistor on, so the resistance must be greater. Okay, part B is the equation that links current, potential difference and resistance again. So again, learning your equation gets you marks in all different sorts of questions. So voltage is equal to current times resistance, or V equals IR again. Do learn your equations. The reading on the voltmeter. So the reading on the voltmeter will be the current through the 20 ohm resistor here, which was 0.3, times the resistance, which is 20. So 0.3 times 20. And remember, whenever you times a number by a decimal between 0 and 1, it will get smaller. So I've got 6 volts, which is good. So state the potential difference of the power supply. And I knew instantly it was 6 volts as well. And there's a rule which allowed me to see that very quickly. So we're going to go back to our circuit diagram here. And you have got three branches in this parallel circuit. You've got this one, and you've just calculated the voltage across this branch as 6 volts. And you've got this one, and you've got this one, which the power supply is on. And the rule is simple. The voltage or potential difference across each branch of a parallel circuit is always the same. So if there's 20 ohms if there's 6 volts across the 20 ohm resistor, there must also be 6 volts across the branch with P on it, and 6 volts across the power supply. So that is one of your voltage laws for parallel circuits. We did it quite a while ago, so I guess I can forgive you if you didn't get that. And just a kind of important note on electricity: no one finds it easy at the start, so please don't be too hard on yourself if you really struggle with this test. Electricity is hard. You've got to stick with it, especially on the foundations here. Loads of kids will be getting nothing on these questions in the final exam. So if you can stick with it and get half of it, you're doing well. And if you can really stick with it and really develop a good understanding, you'll really go on to beat other foundation tier students. Part C, a second circuit contains an unknown component labelled X. As component X is heated, the reading on the ammeter goes up. So how did I know that component X must be a thermistor? Well, there's the giveaway really is that the current goes up. So if the current goes up, the resistance must be going down. And the component that behaves in that way, that reacts to temperature, when the temperature increases, its resistance decreases, is a thermistor. So a thermistor is a temperature sensing device. It has this circuit symbol, which I've got on the answer line to see. And as the temperature goes up, the resistance it provides goes down. For the purposes of this course, give a reason for your answer, and I've said there is an inversely proportional relationship between current and resistance. So an inversely proportional relationship is just a clever way of saying, as one thing goes up, the temperature, the other thing which you're interested in, which is the resistance, goes down. So that's inverse proportionality. As one thing increases, the other thing decreases. So 1 mark for thermistor and 1 mark for explaining why correctly. So didn't really like this question, to be honest. Let's see if I can zoom out a bit. Got a lot of words here, wasn't too hard, but you did take a bit of reading. Complete each of the following sentences A, B, C, D, and E by choosing the correct ending from K, L, M, N, and O. The first one has been done for you. So the first one you've got to do a direct current. So a direct current is supplied by a cell or battery. So all cells or batteries provide direct currents in a GCSE combined science or physics course. A series circuit, the potential difference. Now this relates back to the initial question. So in a series circuit, the voltage, which is another name for potential difference, is always split across all of the components that it's connected across. So in the first question, if you cast your memory back, your mind back, the 230 volts were split across 20 bulbs connected in series, so we had 11.5 volts across each bulb. So the answer to that one was N. An alternating current changes direction, and in UK mains electricity we have a frequency of 50 Hertz, which means that the current will change direction 50 times a second. In a parallel circuit, the potential difference is across each component is the same, and that is the rule that we used for this question here, part 3. Yeah, quite a lot of reading there, I guess, and you needed to have kind of a broad understanding to get the 3 marks. Next one. Looks scarier than it is, this one. Question 4a. The diagram shows the circuit that a student used to investigate how a current through a resistor depends on the potential difference across the resistor. So here's your circuit diagram. Part 1. Each cell provides a potential difference of 1.5 volts. What is the potential difference provided by the 4 cells in the circuit? Now they're all connected in series, positive terminal to negative terminal, so you just add up their individual potential differences. So 4 times 1.5 is 6 volts, so 1 mark for that. The student uses the component labelled X to change the potential difference across the resistor. So what is component X? So if you see a component with a rectangle in, it has something to do with resistance, and the arrow through it indicates a variable resistor, which means that the user can vary the resistance that it offers from a lower resistance to a higher resistance. So 1 mark for variable resistor. The component connected in parallel with a resistor, which is this bit, so is a voltmeter. Stupid question because it's got voltmeter next to it, so actually that question was just testing, do you know what parallel means? So parallel means across another component with 2 connections. Good. Next one. The results obtained by the student have been plotted on the graph. So potential difference on the x-axis, current in amps on the y-axis. One of the results is anomalous, and that means the one that doesn't fit the trend, so you circle that one and you take the mark. Which of the following is the most likely cause of the anomalous result? Put a tick in the box next to the answer. So, why isn't it the voltmeter had a 0 error? Well, if the voltmeter had a 0 error, then this potential difference here would not go through the point 0, 0. It will go through a different point. But it does go through 0, 0, so it can't be that response. The resistance of the resistor changed. Now, if you have on a current voltage or current potential difference graph a straight line, that means your resistance is constant and it's not changing. So that one isn't true. So the only viable answer was the remaining one we haven't eliminated, was the first one. So the student misread the ammeter. So tick that and give yourself a mark. What interval, part 3, between the potential difference values obtained what was the interval between the potential difference values obtained by the student? So what is this asking? So the interval is what the experimenter went up in volts. So they've got an answer for 1 volt, there's a cross there, 2 volts, 3 volts, 4 volts, 5 volts. So what is the interval? How much voltage is between each reading? The answer is 1 volt. So the interval is kind of a scientific way of saying what was the gap between readings that the experimenter went up in. Describe the relationship between the potential difference across the resistor and current through the resistor. So I said directly proportional, and that's just a fancy way of saying as the current goes up, so does the potential difference, or vice versa. As the potential difference goes up, the current goes up. And also the other criteria for direct proportionality is that you go through the origin, which is 0, 0. So 1 mark for saying as the potential difference goes up, the voltage goes up, or like me, using the phrase directly proportional. Question 5, part 1. Draw lines to join the picture to the correct circuit symbols. So this one is a variable resistor, this is a fixed or just a resistor, this is a diode, and this is a lamp. So 2 marks available for that. So it's question 5. Let's just flick to the mark scheme. And will it let me zoom in? No. So you get 3 marks for all of them done correctly. So 1 mark per item. So that's pretty straightforward. Oh, actually, no, that can't be right because it's only out of 2. So that's crazy. So you would get 2 marks if you got all 3 correct, and you'd get 1 mark if you got 2 or 1 correct, and you get 0 if you got nothing right. So are the lamps connected in series or parallel in this next question? So this is a family tent with a simple lighting circuit, a bulb for the living area and sleeping area. Here is the circuit diagram, 2 bulbs connected with 1 loop around and a switch there. So is it a series or a parallel? Well, there's only 1 loop that the current can go around, and that is what a series circuit is. So 1 mark for saying series. Number 2. This is not a good circuit for using in the tent. Why? Well, I said if 1 bulb fails, the circuit is broken, so I got a mark for that. So there was another correct response as well. So both lamps must be on or off together. So let's say that you were trying to get some sleep and some other people in the living area wanted to play cards. This circuit couldn't switch the sleeping area off whilst allowing the living area light to stay on. So a drawback of the circuit. So it's a good tip for improving is writing down other correct responses so that you're learning. So add that in. So this is a different one, and you can see it's a parallel circuit. So the bulbs are on separate branches with separate switches. So 2 reasons, 1 mark for each, why this circuit is better than the last one. Each bulb can be controlled individually, and if 1 bulb fails, the other can still be used, which is good. Another correct response. So switching one on doesn't affect the brightness of the other. So yeah, that's another advantage of the circuit. So question 6, here's another circuit. We've got a battery here, 0.4 amps flowing out of the positive terminal. Remember, the positive terminal is always the long thin one, the negative terminal is always the shorter one. 2 resistors in series, one after another. One has 20 ohms, one has 10 ohms. The current in the circuit is direct current. What's meant by direct current? So the current is always in the same direction. A current that continually changes isn't direct current, it's alternating current. And the second answer is just stupid. Current that travels directly to the component. It doesn't really mean anything. You always need wires, and it's just a silly response, that. Part B, the equation which links current potential difference of resistance is this for about the 4th time in the test, so make sure you know it. Calculate the potential difference across the battery in the circuit in the figure above. So, start off with my equation, V equals I times R. I is 0.4, the current, and the total resistance is 20 add 10, which is 30. So that gave me a potential difference of 12 volts. So I put 12 down. I don't need to put volts here because it's already there for me. So I might take a quick look at the mark scheme on this one. So if you figured the total resistance was 30, you get a mark. If you did 0.4 times 30, you get a mark, and if you got the correct answer as 12, you get a mark. So power. So the power is the current times the potential difference, so it's I times V. So calculate the power out of the battery. So give your answer to one significant figure. So I messed up here. I didn't read that second bit. So I started off alright, put down the equation, put the right numbers in, got 4.8, and remembered my units was watts. Didn't really need to because they gave me the unit. And then I didn't round my answer to 5. I kept it at 4.8, so I didn't follow the last instruction, so I lost a mark. So if you got 4.8, you get 1 mark. If you've got 5, you get 2 marks. So little lesson to me to not get complacent and read the question. Question 7. The diagram shows the circuit used to obtain the data needed to plot the current potential difference graph for a filament bulb. So here is the circuit they used. Here is the result. Here are the results on a graph. Why is the component labeled J included in the circuit? So this is an interesting point. So if you didn't have component J in the circuit, you couldn't alter the voltage across the bulb. So remember, in a series circuit, which this is, the voltage is split between the two components. So the voltage from this battery goes across the bulb and it goes across the variable resistor. You're only interested in the voltage across the bulb, but you can if you increase the resistance of the variable resistor, you would increase the voltage across it and therefore decrease the voltage across the bulb. So you're using variable resistor J as a mechanism to alter the voltage across the bulb, and so you can alter the voltage and measure the current through the bulb. The resistance of the bulb increases as the potential difference across the bulb increases. Why? Well, the temperature of the filament in the bulb increases. So the more voltage you put across a bulb, the more current flows through it, and the more current that flows through the filaments, the bit of wire in a bulb that's producing the lights, the hotter it gets, the more resistance it has, which then decreases the current, or slows down the rate of increase. So the key thing is the filament gets hot and its resistance increases here. So harder numerical questions now. So the bulb is at full brightness when the potential difference across the bulb is 12 volts. The current through the bulb is 3 amps. Calculate the power when it's at full brightness and give the unit. So you know you're going to get a mark for saying that power is in watts. So you can probably put that down straight away. W for watts, the unit of power. So the equation you need for power is I squared, so current squared times R. So you know that the current through the bulb is 3, and you're going to have to square it. So that's something that you know already. What you don't know is the resistance of the bulb. So you're going to have to use Ohm's law, or the V equals IR relationship to find that. So putting down V equals IR here, and then rearranging for R, which is V divided by I. 12 divided by 3 gives you 4 ohms. So you put that 4 ohms back into this equation, and you end up with 3 squared times 4. 3 squared is 9. So 9 times 4 is 36. And we've already said that the answer is watts. So let's just go to the mark scheme. So if you get 36, you get 2 marks, and if you get watts, you get 1 mark. So not an easy question, that. So a 6 marker. So you're always going to get a 6 marker, and this is comparing a halogen bulb and a light emitting diode, and you have to compare the two using the information in the table, and then conclude which one would be best to use. So is it best to use halogen bulbs or LEDs in your home. So the key thing is here, you have to use this data. You don't bother just trying to answer stuff based on what you think or what you do in your own home. If you don't refer to the data in the table, that's game over for you. Alright, you get nothing. So straight away I've done my layout. So I'm going to compare the efficiencies first, energy efficiencies, then I'm going to compare the upfront cost, how much they cost to buy, and then I'm going to compare the average lifetime. So I've got 3 subheadings which scaffold my answer. And in each calculation I've done to back up, to kind of give me some evidence to make my conclusion, I have divided the LED result by the halogen result, and this is going to tell me how many times better or worse the LED bulb is compared to the halogen bulb. So for energy efficiency, I did my 32 for my LED divided by my 10%, and that told me that my LED was 3.2 times more efficient than my halogen. So that's an advantage for the LED. So you're going to save, when you use it, 3.2 more than 3 times the electricity compared to if you use the halogen bulb. So it's far more efficient to use, more than 3 times more efficient, which means you're going to save money, which I've said here, and it's going to be environmentally friendly. So the upfront cost, well, I've got £11.70 to buy an LED bulb and only £1.95 to buy a halogen bulb. So it's 6 times more expensive when I do that, which is a disadvantage of an LED. So it costs six more times to buy, which is a disadvantage for the LED. So last one, the lifetime. So the average lifetime is 36. A comparison, you can divide the LED's lifetime with the halogen's lifetime, and 36,000 divided by 2,000. I actually don't even need to use a calculator because the zeros cancel. So 36 divided by 2 is 18. So actually, if you stump up the extra cost for an LED bulb, it's going to last you 18 times longer than the halogen did, even though it only costs 6 times more. So that's an advantage for the LED. So after I've done that, done my calculations, I then make my conclusions based on them. So a really useful way of making conclusions is saying, on balance, I think the advantages of one thing outweigh the disadvantages that it offers. So I've said the LED advantages in efficiency and longer lifetimes outweigh the disadvantages of upfront costs. So I've used my evidence that I've generated to make a conclusion. All right. So I've also done calculations. So using the data in tables that you're given to make comparative calculations will always push you up into the 5-6 bracket, especially if they're correct. So try and make this bigger. So if you haven't said anything, you get 0 marks. If you just have done a basic comparison, so you've just said, oh, one's more expensive, but the other one, the other one is more efficient. That's either a 1 or a 2 mark response. Yeah, so just simple sentences. If you have compared either the energy efficiency or the cost, and the comparison is clear, then it's kind of pushing you up into a 2 or 3 mark sorry, 3 or 4 mark response. If you have gone into detail, like I did, so I did calculations, went into detail, that pushes you up onto 5 or 6 marks on this mark scheme. We'll point out this is an old mark scheme, so in the current mark schemes for this style of questions, you want to be doing numerical calculations for comparisons and drawing conclusions based on them. Alright, if you're going to really get the best marks. If you found it hard, you know, some students get nothing on those. Some students, you know, quite a lot of students will just get 1 or 2 marks. You're doing well compared to other foundation level students, in my experience, if you are getting like 3 or 4 marks. And if you're getting 5 or 6 marks, you're smashing other people to pieces. You're really beating them, because most foundation students struggle with those style of questions. So, well done. Next one. So the current potential difference graph for one type of electrical component is drawn below. So always, when you have an IV graph, so current on one axis, voltage on the other one, that has 0 volts up to 0.6 or 0.7, and then once sorry, 0 current from when your voltage is between 0 and 0.6 or 0.7, and then the current goes up really sharply afterwards, that is a diode. So you should have recognized the shape of this IV graph as a diode. And remember, they can swap the axes around, so they can put the potential difference on the y-axis and the current on the x-axis. So that's a diode. You should have recognized it from the shape of the graph. How do you generate an IV graph? So this is always the circuit you need for an IV graph. You'll put the component you're testing here. You will have a power source, either a battery or a DC power source or a cell. You will need to have an ammeter in series with your components, and you will need to have a variable resistor to alter the voltage across your component, and a voltmeter to measure the voltage across the component. So 1 mark for drawing a diode and a voltmeter, and the other mark was for placing the voltmeter in parallel across the diode. And the diode should be this way round. So remember, current goes from your positive terminal through your component and into the shorter negative terminal. So the current should be flowing through the larger side of the arrow, and that is the forward bias direction, which is the correct way to set up your diode to get this shape of IV graph. So what was the current when you had 0.8 volts? You had to go up from 0.8 using a ruler, go across and read off from your graph, and it should be 0.048. And then calculate the resistance. So again, using V equals I times R, rearranging for resistance, so R equals V over I, and 0.8, which your question gave you, divided by the 0.048, which you read off from your graph, should give you 16.6 recurring. And I think they allowed a rounded response there, so if you got 0.05, that was fine. Any response between 0.048 and 0.50 was fine. Another way of saying 0.050 amps is 50 milliamps. So that would have got you some marks as well. Question 9, the difference between alternating current and direct current. So I've used a word which is really useful for formal comparisons, whereas. So direct current only travels in one direction, whereas alternating current changes direction. So 1 mark for saying that direct current goes in one direction, 1 mark for saying alternating current changes direction. Last one. The diagram shows how the electric supply cable is connected to an electric kettle. The earth wire is connected to the metal case of the kettle. So this is a heating element, is what gets hot and heats your water in the base of your kettle. It gets covered in lime scale. Your parents probably have to put some chemicals in there to descale it every once in a while. And here is your power cable. Remember, you have 3 cables inside a UK power cable, with an earth, live and a neutral. If a fault makes the metal case live, the earth wire and the fuse inside the plug protect anyone using the kettle from an electric shock. Explain how. So more current will flow through the live wire, the fuse will blow, and the current will travel through the earth to the live wire. So you definitely need to be saying that if there's a fault, the current will increase. Then you definitely need to be saying if the current through the live wire increases, that will blow or melt the fuse. And you definitely need to be saying that then the current will be taken to earth through the earth cable. So they're features of a correct response. Okay, let's just take a look at the mark scheme. So I can make it a bit bigger. It's not even in the mark scheme, which is very interesting. So yeah, you're just gonna have to use my example. So if your response addresses those points, so an increase in current, the fuse melting or blowing, and then the current being taken to earth along the earth wire, that would get you both marks.